All right, so let's use what we learned in this example where the personnel director is asking if I collect a sample of 30 from my pool of managers of 2,500, and what's the probability that the sample mean will be within $500 from the population mean? Okay, so let's see that. And here bear in mind that we know in the background what's mu, we know the population, but now we are just experiencing what would be the power of sampling distribution. All right, in later topics we would not have that mu, and we're going to rely on the sample in order to make the real inference. Okay, but for now we are simply learning the power of sampling distribution. All right, so what do we know about that X bar that would be the mean of that sample? It belongs to a distribution, all right, called X bar, which is normally distributed from the central limit theorem. It has a mu, mean equal to mu, the population mean, and standard deviation sigma of X bar. We calculated these mu and sigma X bar, right, in the previous slides. We got sigma X bar 730 point something, and we can round it easily. All right, so let's see how does it look like. It's a normal distribution. It has a mean of mu. And so what's the question? The question is the probability that this X bar is within 500 from the population mean. So if I want to translate that into a probability statement, I'm going to write that. So I'm asking what's the probability that X bar is greater than mu minus 500 but less than mu plus 500, right? So that's it. You can see it's within plus or minus 500. So let's plug the figures of mu here. I know mu, again, for now, we know mu, and we are simply now here experiencing what's happening when we use sampling distribution. Okay, so the question is, what's the probability that an X bar collected from the population will be between 51,300 and 52,300? Let's see that on the graph. So it's between these two values. And we have learned already that to find the probability of a variable being within the range, that means we are looking for that area, right? And we have learned also from the previous topic, whenever we want to find an area between two cutoff points or boundaries, okay, it's always equal to that. The first term, P of X bar less or equal than 52,300, it gives me all the area from the lower tail until 52,300. We have learned that, so I'm not going to repeat myself a lot. Minus the small area, which is the area from the lower tail to 51,300. So what do you think is the next step? Remember, we standardize. So I'm going to subtract the mu and divide by the standard deviation. But remember, the standard deviation is the standard deviation of this distribution, this one that has a standard deviation of sigma of X bar, right? Because this is the distribution of X bar. So we'll do that to standardize. And here we go. And you know that on the left-hand side, I have only notations, but on the right-hand side, I have real values. So this is the value for an X bar, specific value. This is the mean, and this is the standard deviation, which we know. So now we can transform that into probability of Z, right? This one, the whole thing here, this is Z. We are standardizing that. So Z, and this is a value of 0.68 minus P of Z less or equal than minus 0.68. And now you go to the Z table and you read these probabilities and you get a value of almost 50%. Not bad at all, right? So when you collect a sample from 2,500 salaries and sample of 30, you are 50% sure that the mean that you get from these 30 would be within 500 from the population mean. So now let me tell you that if we don't know the population mean, I have now this confidence, right? and it was important that we plug the value of mu here to let you confirm that. Okay, and remember, in real life, no, we don't have mu, and we're going to use the sampling distribution to make all the inference. So what happens when we select a larger sample? Okay, let's see what results we can get. So we're going to explore a relationship here between the sample size and the sampling distribution of X bar. And this is going to be a very interesting relationship. Okay, so let's consider the case of selecting a random sample of 100. Okay, what do you think? Do you think we'll get a better information or worse information? We learned that also in the beginning of our course, that the more the sample size, the more information you get about the population, right? So this is the intuition here. You should always have that intuition that a large sample, okay, you are collecting about that population, you should have a better information about the population. Okay, so we're going to quantify that. But let's see first what the effect that we get when we change the sample size from 30 to 100. What do you think? What happens to the sampling distribution? Sampling distribution, the form is not going to change because whether it's 30 or 100, it's normal distribution. The mean is the same, doesn't matter what sample size, of course it should be greater than 30, and here it is. But what about the standard deviation? This is the only parameter that changed. We know that the standard deviation, okay, it's a function of n because it's sigma of the square root of n. Yes, sigma does not change, but now n is changing. So what happened now? Instead of 30, we have 100. So the new standard deviation for the new distribution is now 400, almost half of what we have before, right? And this is important because you learned what the effects of standard deviation on the shape of the normal distribution, right? Anyway, let's see it in the next slide. Look at the effects of the standard deviation on the distribution, like we have learned earlier in the previous topic. Okay, we learned that the smaller the standard deviation, the more concentrated is the distribution, right, around the mean. And this is what we see in the blue distribution. This corresponds to sigma of 400, and we can see how concentrated this in relatively to the red one, which is corresponding to 730 standard deviation. Okay, what does this mean? Let me show you. For example, if I take any two borders, okay, these are the same values of x of x bar. Remember, the horizontal line is the axis of x bar. So we know that when I fix this value, I fix this value. Okay, I can use it for no matter what distribution I have on the top, what curve. So what I'm saying here, I need to find what's the proportion of values of x bar lie within this range. If I have the red distribution, I will have this area. Okay, so this is the proportion of the values that lie here. And from the previous example, we could find that this represented what? It represented around 50%, right? And you can see that it's almost up to scale here. So it's 50% of all the values. While within the same range of these two values of x bar, if the x bar follows the blue distribution, then I have all these. And look at that. They make the most of the area under this curve. So I easily can see that this is certainly above 50%, maybe 70%. Let's quantify that. Let's see exactly what would be the change in this area. Okay, so let's see what would happen now to the probability that was asked by the director. But now after we selected a sample of 100, okay, so we know that now x bar follows a normal distribution, and now look at this. Okay, I put it in bold so that you can see it easily, that the only difference is now the standard deviation of the sampling distribution. All right, so that was the question. And as we did before, we're going to subtract and put the values of the mean. So the question is, what the probability that x bar less or equal than this minus probability of x bar less or equal than that? Again, we'll do the same thing. We're going to standardize in order to find these. So we subtract the mean, divide by standard deviation. But again, remember that now we have a new value for the standard deviation. So everything else is the same as in the previous example, except that one. Now it's 400, which of course would have now an effect on that value of z. When the denominator is now less, the z will be greater, right? And as expected, now z's are 1.25 and minus 1.25. And what we can do now, we go to the table, read these areas in the table, and we get 79%. Huge, right? So compared to the previous one, by simply increasing sample size from 30 to 100, now we are able to increase our confidence, okay, from 50 to almost 80%. That's huge, right? So that's a very good boost for our inference.